Coming. This is a subject that I've done quite a bit of research and development on, and I'm continuing to do research and development on this. And in fact, I've done a bit of writing about this subject on the DeveloperWorks site. I've written 20 installments around this subject. You can get to it through this URL, but that's hideous and awful, so I've used modern technology to shorten that and make it more accessible. And so you can read a lot more about this topic there if you're interested in it. My agenda this morning is to talk first about what is software design, what do we mean when we talk about design and software, then a little bit about the distinction between architecture and design. And it turns out there's a particularly useful way to distinguish between those two things that allow you to think about them separately, which is very often a useful exercise to perform. I then talk about things that make emergent design hard. I talk about some things that make it easier. And then I talk a bit about, once you've found these design elements, what can you do with them? How do you harvest them? And how do you take advantage of them? But I'm going to start with the poetry of Donald Rumsfeld, who very famously said, there are known unknowns. That is to say, there are things that we now know we don't know, but there are also unknown unknowns. There are things that we do not know we don't know. And he didn't realize it, but he was really talking about software here. Because this, it turns out, is the deadly thing in software. It's not the known unknowns, because you can make contingency plans for that. You know, we don't really understand how that works, so let's plan some time to research and develop that and think about it. It's the unknown unknowns that end up killing you. And in fact, this is the thing that ultimately kills any kind of big, giant, upfront design effort in software. You always get nabbed by the unknown unknowns. And so, in the agile space, what we've realized is that the future is really, really hard to predict. And in the traditional architecture world, what they've been trying to do for years is make their crystal ball better by applying more and more rigor to it. And we've been doing something different. We've said, you know, the future is really hard to predict. What if instead of getting better and better at predicting the future, we get better and better at adaptability as we go? And then you don't pay quite such a hard price for having the unknown unknown pop up because you're a lot more adaptable. And that's exactly what this talk is about, is how can we build techniques for adaptability into software so that we don't pay these huge prices for the inevitable unknown unknowns that are always lurking right around the corner. But before we get too far into that, we really need to answer a fundamental question. Like, what do we mean when we talk about software design? And fortunately, someone has answered this question for us. Back in the fall of 1992, in the C++ journal, Jack Reeves wrote a very influential essay, which you can still get at that location. It's still worth reading because you would believe that it was written last week. And he makes some very interesting observations in this paper, because what he's trying to do here is do a deep metaphorical comparison between traditional engineering and software engineering. We do lots of light metaphorical comparisons about, you know, our job is like building bridges, or our job is like gardening or mountain climbing, or all these kind of very loose metaphorical comparisons. But he wanted to go a little bit deeper and see how things really are similar and how things really are different. And he reaches some interesting conclusions. The first one being that the final goal of any engineering activity is some type of documentation. If you're a civil engineer and you're tasked with creating a new bridge, what is your outcome for your work? It's a design for a bridge at a particular location that operates under particular constraints, that has particular scalability characteristics, but you don't actually build that bridge. You hand it over to a group of people who are expert bridge builders, and you turn it over to a manufacturing team. And so the output for the engineering effort is this design that you hand to an engineering team that actually ends up manufacturing it. But here's one of the places where the traditional world and the software world differ a lot. Because manufacturing for physical things means stamping out atoms. And it turns out that once you've stamped atoms into a particular shape, it's really hard to unstamp them so that you can restamp them in a different shape. You have to do crazy things to like melt them or change their chemical composition, etc. But we don't live in an atoms-based world. We live in a byte-based world. And bytes are super soft and malleable, and you can change them all the time with a drop of a hat. So it's a very different thing from our world than the traditional engineering world. But then you have to ask yourself, so what is the analog in the software world to that manufacturing process that traditional engineering goes through, it turns out it's the compilation and deployment process that we go through. That's the thing that takes our design and manifests it into something that moves things around in the real world, in this case electrons through wires, etc. Which suggests that our design, our blueprint, our outcome for the engineering effort is the source code. The complete source code. This is our blueprint for software. And any change that changes source code changes our design. Every time you make a change to source code, you're changing the design of your piece of software. So debugging is part of design. Quality assurance is part of design because they make changes that yield changes in the source code. In your software, that is your design. But here's where we really differ from the traditional manufacturing world, because the most expensive process in the traditional engineering world is the stamping out atoms part. In fact, a lot of the techniques of predictability that were created in the traditional engineering world were not created to make things safer. They were created initially to make them more cost effective, because it is simply too expensive to test bridges by building new bridges and rolling heavy stuff over them to see if they collapse or not. That's a terrible way to build bridges, but we can build software like that all day long because there's virtually no cost to remanufacture it. We just fix the little hole and remanufacture the whole thing, and we have a realistic kind of world again. Our manufacturing is dirt cheap. In fact, every time you stop typing now, an army of gnomes inside your computer springs to life and manufactures your design for you. And Jack Rees concludes his essay by saying that given that software designs are relatively easy to turn out and essentially free to build, an unsurprising revelation is that software designs tend to be incredibly large and complex. I think they're likely some of the most complex things that humans create because we don't have some of the same constraints that other kinds of engineering has. For example, we don't have the same kind of locality to fault that traditional systems have. So if a wing falls off an airplane, a forensic engineer can kind of go to where it was connected to the airplane and deduce that there probably is a problem around there. But in software, some little fault can cause an instability that doesn't manifest for 100,000 lines of code away, so it's very hard to trace down exactly what is that problem. It's also extraordinarily fragile. We have very, very fragile breakage points in software, unlike in the traditional engineering world. So the software designs tend to be these giant, large, complex things because we don't have the same kind of failure modes and the same kind of constraints that would keep them simple that exist in the real world. And his ultimate conclusion is that software may be cheap to build, but it's incredibly expensive to design because everything you're doing is basically part of this design process in software. So when he was talking about design, he was really talking about what we talk about now, encompassing all of architecture and design and all the things that make up what you're doing as you create new software. But I want to make a differentiation here between architecture and what I'm calling design. Unfortunately, design is one of those mega overloaded words because Jack Rees uses design as basically what we call architecture and design and all the things that go into software. When we think of design now, we think of user experience design and the kind of user experience interaction. That's not the kind of design I'm talking about. The differentiation I want to make here is one that Martin Fowler makes in his white paper called Who Needs an Architect? And it is actually the basis for the title of the Developer Works series that I showed you in passing earlier. And it's this idea that in his white paper, Who Needs an Architect, which is really a white paper about the role of architects on agile projects, he kind of incidentally gives some definitions of architecture. And one of those is my favorite definition of architecture, and it leads you to this very useful kind of ability to cleave this definition in part, is that the architectural elements in a piece of software are the things that are perceived as hard to change later. And that, in fact, leads to the title of that Developer Works series, I don't know if you noticed or not, was Evolutionary Architecture and Emergent Design. And there's an important distinction between those two things. Because if the architectural elements are the things that are hard to change later, those are represented here in kind of these gray boxes. Everything sits on top of architecture. You can't have emergent architecture because everything rests on top of it. But you can have emergent design. So the gray boxes here in this very abstract picture represent architectural elements. You can't start shuffling those around without making everything unstable. But the things that are sitting on top, you have much more flexibility of moving those things around. And so you can kind of ask yourself when you look at your software stack, what's architecture versus design? If it's hard to change later, then it's architectural. So your language is certainly architectural. The web framework you've chosen is architectural because you can't trivially change that for something later. But the way you're using those architectural elements, so your web framework, the way you're using the workflow and the validation and all those pieces that come with it, those are really aspects of design. And you don't have to get those nearly as correct because the penalty for changing those is not nearly so high because other things don't rest on them and depend on them. So the real trick in this world is, can we build architectural components that are simple enough that we can evolve over time? Because the second half of this definition is, ideally you'd like to have as few of these things that are hard to change as possible. Because architectural elements give you useful scaffolding. It's things you don't have to build yourself. But they also represent constraints. And so what we'd like to have is the most benefit with the fewest constraints. And that's kind of the way we try to design things. And we make this split between evolutionary architecture, which is very much in the kind of microservices, REST, and component-based worlds the previous speaker was talking about, and that some other people in this track are going to talk about later today. I'm going to focus mostly in this talk on this design aspect, and in particular, emergent design. And so let's talk about some definitions. If you look at the word emergence, that's basically the root word of emergent, or vice versa. And the definition from Webster says rising or emerging out of, it says something about fluids, so I'm going to selectively edit the Webster definition to get exactly the one I want, which is rising or emerging out of anything that covers or conceals or comes to light. And there's another Webster definition that says suddenly appearing, arising unexpectedly, or calling for prompt action. Both of these aspects turn out are part of this world of emergent design. And I'm going to talk about two different aspects that I will do a much deeper dive into during the course of this talk. And here's the first one. Let's say that conceptually at your job you have a problem that looks kind of like this. And while you're at work, you're thinking about this. While you're driving home, you're thinking about this. While you're mowing your yard, you're thinking about this. When your spouse is talking to you and you're supposed to be paying attention to them, there's still part of your brain that's still working on this because you know that there's some sort of pattern in all this mess that you really can resolve. And you think about it really long and hard, and finally some sort of useful pattern or hierarchy comes floating out of that. That's really this exercise of taking existing code and finding abstractions and patterns that are living and lurking and hiding in that code. And I'll show you some concrete techniques using metrics and other things to actually go and do this in an existing code base. So that's part of emergent design, is taking existing code base and being able to find design elements that are in there that you just never saw before because you didn't have a particular light that you could shine on that corner of your code base to illuminate that little design issue. So that's one half of the techniques I'll talk about. The other half is this concept from the lean software guys of the last responsible moment to make decisions about things. And the idea here is that very often on projects you're presented with a decision, you should ask yourself, is there a way I can responsibly defer that decision until later? The idea being that the longer you can delay that decision, the more real knowledge and context about the true nature of the problem, not what you think the problem is, but the actual problem, the longer you can delay that, the more real information you can work on, and you have a potential for a better decision. Of course, you can't wait too long, and that's the tricky thing, is the last responsible moment. But the longer you can delay, you have more real data for a decision. And so the trick here becomes, how do you find that inflection point of the last responsible moment? I'll talk about a few techniques about that toward the end of the talk. And so I'm going to talk about these two aspects of emergent design. And it turns out that these two very nicely fall into two categories. Finding abstractions and patterns works really well on existing brownfield projects. And last responsible moment works really, really well on greenfield or brand new kind of projects. And in fact, some of the current research I'm doing is, and I won't get to in this talk, I'm just tease you for the next talk that I'm going to do at some point in the future, is exactly when does the inflection point change from greenfield to brownfield, and your engineering practices should change as an inflection point passes from greenfield to brownfield, because when that inflection point happens, you now have different engineering concerns that you did from when it was a greenfield project. Oh, and here's the white paper that I was talking about, that I alluded to before, from Martin Fowler. That's the Who Needs an Architect white paper that I've talked about. So, I'm going to talk about some things that make it so you can find design elements, but I'm going to spend a couple of minutes and talk about what is unfortunately much more common in our world, which are things that make finding design elements in code hard. I'll talk about three things, and first of these is the nature of complexity in software. We have two kinds of complexity in software: essential or intrinsic complexity. Every problem has a certain amount of essential complexity that is part of that problem. But we also have a lot of accidental complexity, which are all the truly innovative ways we have figured out how to make problems way harder than they should be, which seems like the most fruitful area of innovation in software, is how can we make things ridiculously complex, because we're really, really good at that. This is not a new distinction. Fred Brooks made this distinction back in 1975, and we still struggle with this. But a lot of understanding design is understanding, am I looking at essential versus accidental complexity? Because obviously accidental complexity is design that shouldn't be there, and so sifting through that is one of the initial things that you're going to have to do to figure out, well, is this something that needs to be preserved or should it be gotten rid of? The second thing that makes emergent design really tough is rampant technical debt everywhere. This is a metaphor by Ward Cunningham that I'm sure you're all very familiar with, because it's a metaphor that works really nicely in the real world. The idea here being that if you look at, if you can imagine your software that you're working on right now, but you could lavish all of your love and attention on it. There's no refactoring too big or too small. You can do anything that you want to make it the most perfect software on earth. Think about that, and then the version of it that you left to come here, the delta between those two things is largely going to be technical debt, which are generally externally imposed forces that cause you to compromise design elements. Schedule pressure is the classic kind of technical debt driver, but there are others on projects. There's a famous one called the boat anchor anti-pattern, which says that we paid a lot of money for this framework or this infrastructure, and thou shalt use it on every project, whether it makes sense to use it on this project or not, because we paid a lot of money for it. That drives a lot of technical debt on lots and lots of projects. The standard corporate database often drives technical debt on lots of projects, because we all use the same database for everything. And so congratulations trying to get your network graph through Oracle. See if you can ever get that to happen. This is really a reality in our world, this idea of technical debt. And in fact, I don't think it's necessarily a bad thing. Just like credit card debt, for example, is not necessarily a bad thing, but fortunately there's a real world governor on credit card debt called a credit limit. And that's the thing that most software projects lack, is a credit limit. And so the real trick on technical debt is not avoiding it. I think it's actually unavoidable because of the nature of how business interacts with the way that you build software. The real trick for us is negotiating repayment. But before you can negotiate repayment, you've got to convince someone that technical debt exists in a way that they can understand. It's one thing to go to your boss and say, you know, I'm starting to feel sick inside, I'm having trouble sleeping at night, I think our software might be starting to suck. And they're going to immediately ask you, well, how can you tell? Well, I'm going to show you how to tell. And one of my mantras in the agile engineering space is that demonstration trumps discussion. You can talk about this stuff until you're blue in the face and you'll never make any headway, but if you can start showing objective results, this is the outcome of engineering, about repeatability. If you can find something that shows your case objectively, then you can go a long way toward convincing them that some exercise, like we need to spend some time refactoring, is a useful exercise to undergo. And I want to show you a really nice technical artifact that illustrates technical debt. But before I do that, I need to digress for just a second and do a little background on a particular metric called cyclomatic complexity that many of you are no doubt familiar with. This is a very old metric that's been around since the 1970s. You also hear this called McCabe's cyclomatic complexity because Thomas McCabe created it. But the idea here is that you can place a numeric value on how complicated a function or method is. And here's the formula: edges minus nodes plus 2, where nodes are lines of code and edges are possible pathways through code. So if you look at a simple little method like this, and you draw it out in this edges and nodes kind of view, you can count things up. This is 4 minus 4 plus 2, so this has a cyclomatic complexity of 2. But it's kind of boring when the two cancel each other out. So here's a slightly more complex method or function, and you can label it with the edges and nodes view and find out that the cyclomatic complexity of this guy is 3. So this is one more complicated than the function that we saw before. So we now have a tool that lets us run it against our code base and assess what the most complex functions are, which is kind of handy. And we'll take advantage of that a little bit later to go find some complex things so we can kill them off. But we can also generate some other interesting facts from this metric. For example, because this is a function or method level metric and your system is composed of classes that consist of many methods and functions, you could run this against your whole code base and get a complexity number for the entire code base by aggregating all those together. And if you divide that by the number of lines of code, you get cyclomatic complexity per line of code, which is a very interesting metric because you can see trending. So here's a chart that was created by one of my colleagues on a project that was a public-facing media site in the UK. This is a snapshot of this project in time from April 1st, 2006 to August 18th, 2007. The red line that you see there is cyclomatic complexity per line of code, and the gray boxes you see are releases of this code. And the interesting thing here is what happened around release number 3. Because they were hurrying to get this out. They had a lot of schedule pressure. And it manifests here in churn in complexity because they're adding complexity and they're killing it off and they're adding it because they're in a lot of hurry and there's a lot of churn on the project. And the tech lead on this project realized this trend was happening and so produced this graph. And he did it by hand by writing a little Ruby script, ran a complexity tool on the first version, and then check out the second version, run the complexity tool, aggregate the results, and then have Excel graph it for you. You can do this more easily with something like Sonar, which I'll show you in a second. But he took this as evidence to the project manager and said, okay, look, where they were release 3, there's a disturbing trend here. Because very often in the software world, the raw values of metrics are not that meaningful. Because you have a method that has a cyclomatic complexity of 12, was that good or bad? Well, I don't know. It depends on, is that essential or accidental complexity that's making it that high? But trends are often very interesting because if it's 12 now, and then 2 months later it's 20, and then 3 months later it's 35, clearly something's going in the wrong direction. And that's exactly what he assessed here, was the trend looked kind of disturbing. But you have to ask yourself, so what's the impact? What if we just didn't care about that? What if we just let this run rampant and let this trend line keep going up to the moon? What ultimately is going to be the downside of that? Well, the downside of that is that you're adding more stuff in there that shouldn't be there in terms of technical debt, which means that everyone's velocity is going to slow down just a little bit. Because now technical debt literally means things in your code that shouldn't be there, that are compromised for what should be there. So when it comes time to add other new features later, you have to go back and refigure out why this weird thing is there and then build around that compromise, frequently by building another compromise around that. And so it's like you have a garden where you have weeds growing up and it becomes very hard to find the vegetables for all the weeds over time. So the long-term impact of unaddressed technical debt is that everyone's velocity gets a little bit slower over time. In fact, some of you may have seen this manifest at your company where changes that 2 or 3 years ago would take 2 or 3 days now take several weeks because you have so much technical debt built up. And in fact, this becomes the basis for a pretty good argument to say, you know what, it's not a bad idea, particularly in code bases that have been around for a while. They inevitably accrue technical debt, no matter how careful you have been at designing them, because unknown unknowns always manifest. Having a dedicated resource, a pair of rotating developers, for example, that do nothing but go and kill technical debt is a useful thing to have, because if they're successful, they increase everyone's velocity just a little bit. So their impact is greater than the impact of just 2 people touching code, because they're clearing away underbrush so that other people can can be effective at writing code. And that was convincing enough to say, okay, we need to do some refactoring exercises, and that basically was 3.0 and 3.1 with the efforts to kill off some of that technical debt. This is a good example of this idea that demonstration trumps discussion, showing hard facts. Very often makes an argument that you can at least get some leeway to try some resource allocation or to get some time or something like that. Now, the person who produced this, it was a very laborious kind of hand-created process. You can often get similar kinds of rich visualizations from tools like in the Java world. Sonar is this freeware metrics tool that gives you lots and lots of visualizations, including cyclomatic complexity. Pretty much every structured language in the world has a cyclomatic complexity tools that you can get and find out. So that's a pretty useful metric, and I'll talk about another one in a bit called one of the coupling metrics. So those are both things that make emergent design hard. Let's talk about some things that make it easier. Some accelerators for emergent design. And one of my favorite accelerators for emergent design is the use of unit testing and test-driven development as a way of driving better design by creating less complexity, by eliminating mistaken assumptions that creep in very early on, and they're very hard to spot after the fact. But it's very easy for me to say this, but I wanted to illustrate this idea. So what I wanted to do is take a very simple little problem and solve it in two different ways. I want to solve it first by doing test after, just write the code and then write tests for it. And then I'm going to derive the solution using test-driven development and see what the differences in the design of those two chunks of code are. And I chose for this my favorite little problem. There's a very simple little problem that has a little bit of meat on it. There's this ancient thing that the ancient Greeks first discovered. Is this thing called a perfect number. It's a number where the sum of the factors equals the number if you don't include the number itself. So 6, for example, is a perfect number because its factors are 1, 2, and 3. And if you add 1 plus 2 plus 3, it equals 6. 28 is also a perfect number. If you want someone to factor it and add the numbers up, you can verify that it is, in fact, a perfect number. So that's what I want to do, is write some code that determines perfect numbers. And so I'll do this in Java. And here's my first pass at a test after version of this code. And so what I'm going to do is come in and say, okay, well, I know that 1 and the number are always part of the factors of the number. And now I'll go from 2 up to the number. And if number mod I equals 0, that's the mod operator in Java. So if I goes into number with an even remainder, then it's one of the factors. You add it to the list of factors. You sum them up, and then you decide if it's perfect or not. And I wrote tests for this, and it works. But it's really slow, like crazy slow. And so I thought, well, there's got to be some way, there's some inelegance here. So is there a way I could optimize this? It turns out you can easily optimize this piece right here by making the observation that factors always come in pairs. So if your target number is 28, when you grab 2, you can also grab 14, because 2 times 14 is 28. And so you can take advantage of that fact by saying, well, let's harvest them in pairs. And that means I don't have to go all the way up to the number if I'm harvesting them in pairs. I could be much more clever and just go up, for example, to half the number. But I can be even more clever than that and just go up to the square root of the number, because that, by definition, is the number times itself, which equals my target number. If I grab all the ones below and all the ones above, then I have them all. And that's exactly what I do. I change my code to only go up to the square root of the number. I harvest them in pairs, but it breaks one of my unit tests, because I have an edge case for whole number square roots. So you think about 16, for example. When I grab 4, I'm going to grab 4, and then I'm going to grab it twice. So I end up adding 4 twice for a whole number square root. But that's easy enough to fix. I know that edge case, so I'll just put a little guard condition here that says if this is not a symmetrical square root, then add it to my list. And this now works, and it's considered fast enough to consider, okay, it's done. So that's the test after version. You've seen the algorithm, so I'm not going to go through in the test-driven version. The test-driven version actually has lots of very small methods, which is very characteristic of TDD code bases, because the act of doing TDD itself encourages you toward very small methods that are testable. Your goal is the smallest method that I can test and make work. In fact, given the metric that I showed you before, I'll make kind of a bold pronouncement here, that if you'll show me one metric on your code base, I'll tell you if it's a proper TDD code base or not. Because in my experience, good TDD code bases typically have a cyclomatic complexity per method between 1.5 and 2, and non-TDD code bases, it's generally between 8 and 15. So it is often an order of magnitude higher per function in terms of complexity in non-TDD code bases because there's no external force trying to force you to keep them simple, and they tend to expand on their own, by their own volition. And this also means that TDD code bases tend to have a particular shape in that lots of very small methods feeding into larger aggregating methods. But along the way of doing that, I discovered something interesting. Because in my test after version, I'd been keeping the factors as a list of numbers. But does the order really matter when I'm collecting factors? Turns out it doesn't. Order is irrelevant in the factors. It's a set of numbers, not a list of numbers. And I discovered that from one of my little test breakages that said, I was expecting 1, 2, 3, and 6, but I got 1, 6, 2, and 3, and it made me realize, oh, the order doesn't matter here. I should be using sets and not lists. But then you go back to the two versions of my code. In the test after version of my code, did this really have anything to do with whole number square roots? Turns out it didn't. It had to do with the fact that I chose the wrong data structure initially. I chose an ordered data structure instead of an unordered one. And when I got that test breakage, in a perfect world, I would have gone back and reevaluated all my decisions all the way back to the beginning of time to see where the mistake lie. But you never do that, especially when you can see an easy Band-Aid. And that's exactly what I did, was apply this easy Band-Aid. And so what I did was by choosing the incorrect data structure initially, I added accidental complexity. And the way that I fixed it was to add even more accidental complexity. Because very often, that's the way you end up fixing one piece of accidental complexity, is creating an offsetting piece of accidental complexity rather than removing the original source of the problem. Very often, TDD gets you to the original source because it forces you to vet your assumptions at the method level, not at the entire algorithm level. And it gets dangerous if you're trying to vet things at the very coarse-grained level because you never are forced to go back and vet your decisions at the really, really granular level. And a lot of times, little accidental complexity can creep in because of that. So that's a good example of the kind of emergent design technique on a greenfield project where you're doing TDD, and you can use that as an aid for doing design. But let's talk about the flip side of the coin, which is the kind of brownfield project, and refactoring toward design. Now, this is a little snippet of code that comes from this little toy e-commerce site that takes things from shopping carts and puts them into orders. And I would like to see if there's anything interesting in here, but I can't tell because it's just a giant, ugly pile of code. And if I can't read it, then I can't pull anything useful out of it. So before I can really do anything useful with this, I need to do some refactoring on it to get it organized so that I can see what's actually going on here. So I'm going to make a refactoring run on this, and notice that a bunch of these statements, like these 3 or 4 statements here, are really all about sort of setting up plumbing for the transactional stuff. So I'm just going to kind of scoop them up in my IDE and say extract method. And I'll do that for several of these guys. They're kind of related to one another. And get to this intermediate state here, which is slightly better, but I can do a lot better. But notice a weird thing has happened here. Because I have all these local variables defined up here, my refactoring tool has a very specific contract with me that guarantees that once it's finished, my code will still work exactly the same way it did before. And if I have local variables like this and I'm extracting method, the only thing it can do is pass them as parameters. And so a lot of times you try to extract method in one of these complex functions like this or methods like this, you end up with these giant number of parameters being passed around because that's the only option it really has. Fortunately, you as a human understand the implications of moving things to a class level scope versus a local scope and threading and visibility and all that stuff. And I'm a human that understands that. So I'm going to make another refactoring run, consolidate a bunch of these things in shared places, and end up here. This is the exact same code. And the motivation for this style of refactoring comes from kind of an interesting place from the book Small Talk Best Practice Patterns by Kent Beck, because he calls this kind of code composed method. The idea in composed method is that every public method reads like an outline of all the things that it does, and those outline elements are the private methods that get that work done. And notice that's a particularly powerful kind of pattern for modern IDEs, because all the modern IDEs, function names or method names become hyperlinks when you hold down the control key, so you literally can browse your code if you start with a public top-level method and drill into the individual methods to see their details if you want to, but you're not forced to deal with their details all the time. And now that I've got it down, boiled down to this very simple state, it's trivial to see what's going on. And in fact, if I knock out these two very specific lines of code here, then I have the kind of template for doing a transactional data little framework thingy that I'll extract in a second as I talk about what to do with these things as you've discovered them. But before I do that, I want to do one more refactoring exercise. And for this one, I need one more metric. Talked about cyclomatic complexity before. Now I want to talk about afferent coupling. This is two of the coupling family. Afferent coupling are the number of incoming connections to a particular artifact, either class or package. And so in this particular scenario, this guy has an afferent coupling of 6. The flip side metric to this is efferent coupling, which is the number of outgoing connections. And the way to remember this is that efferent starts with an E, which is also the first letter of the word exit. And those are the exiting calls, whereas afferent are the incoming calls. And so in many ways, if you look at a class, for example, its afferent coupling is a measure of importance, because if a lot of other classes use it, it's probably pretty important. So now I have two weapons. I have a metric that can tell me complicated things, and I have a metric that can tell me important things. Let's go find complicated important things, because that sounds like a good thing to find. So what I wanted to do is take an existing code base and see if I could use some of these metrics to go find unharvested idiomatic patterns that are lurking around for a long time. But I wanted it to be a publicly available code base so other people could reproduce this. It needed to be around for a while and used for a lot of stuff. And so I chose struts. Very well-known web framework. It's been around for more than a decade. It's in its second major release. Literally thousands of web applications, including industrial strength websites, have been built on top of this. And it's my contention that every piece of software has unharvested little idiomatic design patterns in it. So let's go see if we can find something interesting in Struts code base. So I download the Struts code base, I ran a metrics tool on it that gives me my two metrics, cyclomatic complexity and afferent coupling. The tool I used, if anyone's interested, is this little freeware tool called CKJM that runs the Chittimer and Kimmerer object-oriented metric suite on Java code. That's the CK and CKJM. And the way that it reports cyclomatic complexity, because it's a class-level metric tool, it reports cyclomatic complexity for the class as the sum of the cyclomatic complexity of all the methods, and it calls it weighted method complexity. And here are the results for struts. And so it turns out the champion, most complex component in all of struts is this double list UI bean guy with a 66. So if you add all the cyclomatic complexity of all his methods up, it's 66. So if I were just doing complexity hunting, I would go after that guy and try to kill him off or make him a lot simpler. But when you look across, he's only used by 3 other classes. And so Herculean efforts here might clean that up a lot, but it's not going to have a lot of ripple effect to other parts of my code base. Let's sort them by importance instead. And not surprisingly, component is the most important one in Struts, being a component-based web framework. But that's not even the one I'm looking for either. What I'm looking for here are high combinations of numbers. Remember, I'm looking for important, complicated things, and I want to find out why they exist. And the one that catches my eye here is this UI bean guy with a 53 and a 22. Important and complicated, so let's go see why. So I open up the double list UI bean, and I find this lovely guy. He evaluate params. My very favorite part of this method by far is the very last line of the method, which is evaluate extra params. It's like the developer just got tired of typing at some point. Oh God, okay, evaluate extra params. Okay, I'm done. So what this code does, struts is a component web framework, and it sometimes does magic automatic things with URI parameters, and sometimes it just passes them through invisibly, and sometimes it lets mappings happen on those guys. So that's evaluate params and evaluate extra params. And as I started poking around in struts, I noticed that lots and lots of these evaluate params, evaluate extra params methods were showing up, and so I got really curious. And of course, you can do this in IDE, but I did it on a command line with a little bit of command line judo. And I said, starting with the root of struts, give me all the methods, or give me all the Java source files, and find all the ones that have a declaration for evaluate something params. And here they are. I have found an idiomatic pattern in struts. And this is a perfect example of an idiomatic pattern because 15 years ago, when they started working on struts, there's no way they said, you know what, in 15 years, the most complicated part of struts is going to be how we handle URI parameters. Because it's such a simple problem. It's so simple, in fact, they re-implemented it over and over and over and over and over again in the code base without realizing that that was manifesting all over the place. So there's an interesting epilogue to this story. I wrote this analysis up in that developer work series that I was talking about, and one of the struts developers contacted me and said that he had independently discovered the exact same thing had manifested in the struts code base, and he was in the process of fixing it by extracting all that URI parameter handling stuff as an internal component of struts. So if you look at struts now, URI parameters are handled by this internal component, and by doing that, he knocked off several thousand lines of code and several hundred complexity points out of struts without changing the functionality of struts. He just greatly simplified it because no one had ever used that particular lens to illuminate that part of the code base. It's like, oh, this duplicated code is running around all over the place, but you literally just couldn't see it because it's lurking and hiding behind all the other stuff that's there. So once you've found these things, what do you do with them? How do you capture them? And there are a couple of easy ways to do this. One easy way to do this is just capture it as an API. This is the simplest way. This is the unit of how you capture things in the Java world. So in the example that I showed you before, this idiomatic unit of work, this is the code that I want to capture it from. So in Java, I can very easily come in here and say, well, let's use a proper gang of 4 design pattern here. We'll extract this using the command pattern. So now my command's up there, and this is now my method. It's probably worth noting that the entire slide full of code that I showed you before, this is what it ended up being, is this one method right here, after all the useful reusable stuff had been sucked out of it once we determined what the useful reusable stuff was. And in fact, if you look at this, this little wrap-in transaction thing looks a lot like Spring's do-in transaction little wrapper that does basically a lot of the same stuff. Java forces a fair amount of syntactic noise on you because really all you want to do is this, wrap this stuff in a transaction. And languages with higher order functions like Groovy and of course Java 8 are going to make that a lot cleaner and simpler because you get rid of the middleman class that's only there as a holder for that execute method. And so, for example, in Groovy, if you wrote this exact same thing, it'd be a lot cleaner because this, anything curly braces in Groovy is a code block, and that gets passed up here, and that's syntactic sugar for executing it. The exact same thing you can do in a language with higher order functions, and so that actually cleans this up a lot. And that turns out to be a pretty important thing. Syntactic cleanliness is really important because your code is your design document. And so design and readability are very closely intertwined with one another based on what Jack Reeves was saying. So readability makes a big difference. The other way you can harvest these guys in languages like Java is use annotations. I don't think people use this quite enough. This is actually a very powerful mechanism in Java because it adds an extra level of expressiveness to the language that you normally don't have, which is a really nice thing to have, but I won't spend any more time on that. A lot of frameworks use this, but not a lot of developers use this mechanism, and it's not suitable for everything, of course, but the nice thing is that annotations live very close to the thing that you're trying to modify, and so there's a nice kind of locality to the modifications that you're making. I want to talk just a second about abstraction styles because I mentioned the F word, the functional programming word here, as I mentioned lambdas. We're all interested, are all familiar with imperative programming languages. Structured and modular and object-oriented are all styles, imperative abstraction styles. But you hear a lot about functional programming these days. Realize that that's really just a different palette of tools. It's literally a different toolbox. And neither one is particularly suited to solve every problem better than the other, but a lot of times using one is more suited toward a particular kind of problem because it matches the essential complexity better than another one. And we end up getting caught up a lot in the kind of underlying paradigm the language supports because it is the default way that things work. But you don't have to get caught up in that. And a great example of that is this concept of an anti-object that comes from a paper that was delivered at Uppsala in 2006, I believe, called Collaborative Diffusion. And they created this concept of an anti-object. In their paper, they say the metaphor of objects can go too far by making us create objects too much inspired by the real world. An anti-object is a kind of object that does the opposite of what you think it should be doing as a way of modeling something that's simpler. Kind of like this optical illusion, is this a vase or is it two faces? And the classic example of an anti-object approach comes to us in the form of Pac-Man. Now I have to warn you, I'm about to explain how Pac-Man works. If you want to keep playing Pac-Man and enjoy it, you should leave now, and I will understand. Sometimes knowledge comes at a cost, and the cost for this is you're not going to enjoy Pac-Man quite as much, because I'm going to explain the algorithm to you. When you think about the Pac-Man console game that came out in the early 1980s, they had less memory and processing power than most watches have now. And they had a really hard problem to solve, is how do we calculate the distance between two moving objects in a maze? They didn't have anywhere nearly enough processing power to do that. So they took an anti-object approach to this. Rather than build intelligence into the ghost or into the little Pac-Man guy, etc., they built all the intelligence into the maze. The maze is basically a state machine that for every cell it runs rules for every time through the game cycle. And they invented this concept of Pac-Man smell, that when Pac-Man is sitting on a cell, it has maximum Pac-Man smell, and the cell that he just vacated has maximum Pac-Man smell -1, and it decays really quickly. And all the ghosts do is wander around semi-randomly until they encounter Pac-Man smell. They go to the next adjacent cell where it's stronger, and they move slightly faster than Pac-Man, and that's the whole game. Pseudo-random numbers and Pac-Man smell. And they did a really sneaky thing to you. Because the ghost, they gave them eyes, but they should have only given them a nose. Because they can't see you coming. You can run right up on them, and they can't see you, but they can smell where you've been. So the ghosts really need giant noses but no eyes, but they tricked you by putting eyes on them. But now the next time you play Pac-Man, you can run right up on a ghost, and unless he just randomly turns towards you, he doesn't know you're there because they can only follow you. But this is a great example of taking a design that was too complicated to build in the tools they had at the time and coming up with a way of flipping the abstraction over backwards and being able to build something. And when Miss Pac-Man came out, they kept the same algorithm, they just made the random number generator better. So a lot of that's in this place of finding and harvesting idiomatic patterns. But I want to go back for a second to last responsible moment and talk about how do you determine this inflection point. So if you look at complexity over time on projects, and you look at particular components as part of your architectural stack, you will notice that over time they take on varying degrees of responsibility. And at those inflection points where they're taking on more responsibility or making serious changes to them, that's the time you reevaluate it and say, have you reached your last responsible moment? And so this actually goes toward one of the characteristics of architects on agile projects is they need a much better awareness of kind of current events of what's going on in the code because they need to be able to make these kind of determinations. Have we reached the last responsible moment? Has this component started taking on too many responsibilities? We're also big fans of doing spikes, which are experimental coding exercises to determine, to get rid of uncertainty for things like estimates. There's another really famous anti-pattern called the give me estimates now anti-pattern. And the way this pattern manifests is that somebody asks you to estimate something and you don't know anything about it, like tell me how much it's going to take to add geocoding to this application. And the really dangerous thing here is to guess, because the give me estimates now anti-pattern says that as soon as numbers come out of your mouth, you have inadvertently entered into an ironclad contract that you'll risk your life to make that date come true. No matter how many waffle words you put in front of it, spikes allow you to get away from that because you can now look at and determine and get rid of some of the uncertainty that's leading to the speculation as to how long it's going to take to do this. So to summarize, obviously, evolutionary architecture and emergent design require good engineering practices. If you have a good TDD code base, you can do refactoring on. It makes it much easier to do these exercises on. It doesn't preclude you from doing them, but it certainly makes it a lot easier if you already have good other engineering practices. There's the most advanced engineering practice, which the architecture and design space becomes easier. Trying to predict the future leads to over-engineering, which is a bad thing. And this is going to be a subtle distinction, but I think a really important one. Because in the agile world, we're trying to prefer being pro and reactive to predictive. We're not trying to predict the future. What we're trying to do is be proactive about things we know are going to happen in the future, and then being instantly reactive as things happen in our code base that we need to be able to respond to. The combination of pro and reactive, I think, works much better than trying to get better and better at predictive, because as any street corner psychic will tell you, trying to get better and better at predicting the future is really, really hard to do. I'm out of time, and I don't want to cut into lunch because I know that's a very important agenda item for many of you. I'll be here for the rest of the week if you have any questions or anything like that. Thanks very much for coming, and hope you enjoyed it. Thank you.